Thank you. All right. Yeah. All right. So, today we're talking about um, how to make how to make images come alive with Scikit-image, and basically how to process image using Scikit-image. Yeah. Last time I was supposed to take a breakout session, but I didn't get a link. I couldn't join early, but I wanted to do like a a quick walkthrough on a project, which was the last project you guys did on rent house. But that would be maybe later, Sha. But let's just move on with this instead. So what is image processing? First, to understand what image processing is, we need to understand what image itself is. An image is an array of matrix or square pixels, and these pixels contain information about the color and intensity of images. And the second question now is, what is image processing? Now, image processing is basically like an operation we do on images, just like we um, make operations on numbers or uh, sentences or even data itself. So if we have images as our data, how can we get information from this image? How can we process this image to be able to understand it and get the necessary information we need? So image processing is used to enhance images, is used to also extract useful information, and then it's also used to analyze the yeah. Um it is used in different sectors or area or profession, from medical image analysis to AI, image restoration, um, surveillance, basic for surveillance, robotic vision, and also automotive safety and so on. So automotive safety, like um, our autonomous cars that we use, most autonomous cars, they need to be able to identify what they see while on the road. So we use image processing for that. Now, yes, this is an image, and this image is in grayscale. Now, the threshold is basically in binary. So every part that is white is represented as 1, and every part that is black is represented as 0. And the histogram is a bimodal histogram. It helps to show how light or how dark our images is. On the left, most times on the left, we always have, it shows that it has more a darker, some part of the images are very, very dark. And then on the right, it shows that some part of the images are light or bright. And then this one right here shows that the darkness is more than the lightness of the images. Now, these are the applications I already mentioned, which is for medical analysis, artificial intelligence, image restoration, and AI. So this is an example of the medical analysis we use in images. So we have like MRI scanning in most hospitals, and they use it to scan the brain to see how it looks like, or if there is like something in it, stuff like that. So basically, most times it's always blurry, and image processing helps to enhance it and also segment it for them to be able to process the image and extract useful information from it. Now, this is an example of this one here is an example of face detection. So basically, this also detects a face in an image. And then this is an example of the automotive safety. So the automotive safety helps to um, look at cars that are coming either in front of you or behind. So before I move on, I want to know that everyone here are following up with what I'm saying. can just react if you're following. All right, just one person is following up. So let's just move on. Um, so yeah, what is the purpose of image processing really? The purpose of image processing is for visualization, image retrieval, and they also use it to measure pattern in an image, and also for image recognition. It helps the computer to know um what the image is or what the image looks like. So for visualization, objects that are not visible. So it helps to check, for example, if you put a blurry image in the computer, you can use visualization to be able to know exactly what's in that blurry image. And then image sharpening and restoration. Sometimes we have like images where, let's say, a part of our body is no longer there, or someone is no longer in that photo. We can use Scikit-image to restore those those parts of the image. And then we also have image retrieval. This helps to seek for the image of interest. So image retrieval is basically like when you have an image, and in that image there are different subjects in that image. For example, we have buildings, we have people, we have cars. So image retrieval is basically saying, okay, I want to be able to take the only information I need from this image are the people or the cars or just the building. Help me identify which of them is the car, which of them is the person, which of them is the building. Now, measurement of pattern. It measures various objects. It helps to measure, for example, now, if we have a dice thrown and then we take a picture of it, we can use that picture to identify how many dots are like shown on the dice, or what's the length of the line or the edges of the dice. And then we also have image recognition. It helps us to distinguish objects in images, to see which image is which, or which what is in an image. So what we'll be using today for image processing is scikit-learn. And why is Scikit-image, and they use Scikit-image because it is easy to use, and it has a lot of like complex algorithms that can help us make the workflow faster, and we make use of it in machine learning. So yeah, I already explained what an image is, and I said an image is an array of matrix of squares. And these pixels contain information about the color and intensity. So if you look at this image of the day, if you look closely at it, which is currently zoomed in with this, you'll notice that there are boxes. Now these boxes are matrices or arrays of matrices, and each of these have different information. Now, the pixel information contains information about the color of that part and also the intensity, how bright or dark it is. Now, here's another example of image, or here's what really shows what an image really looks like. So this is the image, right? And each of these image has a box, and each of these box has intensity and intensity and the color. The color is basically black and white here. And from the look of it, we can see that this looks like a face, or like in black and white. And these numbers here are just like the values for the color of that image. So the values really, they start from 0 to 255. 0 means uh, very dark, and then 255 means white. So the less number we have, the darker that box is. And if you guys notice, we have 6 here, which is like the lowest number, and it's very dark. And then we have 110, which is kind of in the middle, and it is gray. But then the one that is very bright, which is 137 or 39, is white. So that's what those numbers basically mean. But most times they are just represented as numbers alone to us. But here we are able to see what those numbers really represent. Yeah, so before I move on, I want to be sure that you guys are following me. Yeah, are you guys following? Hello? All right. Makes sense. Yeah, so let's move on to actual practice. So basically, this code here helps us to import some data. Now, what's this data? The data are basically images. Now, in Scikit-image, we have some preloaded um, images, just like we have some preloaded data set in what's it called? In I think NumPy or Scikit-learn. Yes, Scikit-learn. So this one is for Scikit-image. Now, it can be any type of image, but here we are using Rocket image. And you can import the image by just saying Scikit-image imports data, and then Rocket equals to data.rocket. Now, um, you can also use this on your Jupyter notebook or even VS Code. But first, all you just need to do is install the Scikit-image module. Yeah, let's just move on. So we have two colors we have two types of colors we work with in Scikit-image, which is the RGB channel and also the grayscale. Now for the RGB channel, it just means red, green, and blue. And the red, green, and blue is what makes up the complete color of the images. And yeah, let's just move on. So here is an example of the grayscale image. Basically, it was just zoomed in and we have these numbers. I already explained what these numbers are. The numbers are just the intensity of what that box has. So 230 means it is dark because, I mean, 230 means it is white or bright or light. And then 99 means it is dark. So from these numbers that we can see here, we will notice that that part of the image is not dark, but rather it is bright, very bright. And just like the way they zoomed in, most of the part of these images have the same data. Yeah, let's just move on. So most times before we can work with an image on Scikit-image, we always need to convert them to grayscale image from RGB. And for us to do that, there is a simple algorithm that helps us to that. So we don't necessarily have to manually do it. Now, first thing you need to import the color module or the color function. And to convert to grayscale, all you just need to do is color dot RGB to grayscale. And then in the bracket, the only um the only parameter I need is the image itself, the name of the image. Now, for us to visualize our for us to visualize our image, all of this here is a predefined function that helps us to show an image. Now, you don't have to know this because it is just an algorithm, or I mean a function that we already have in the code, or like most Scikit-image already have. So when you type show image, the name of the image, and what you want to name the image, like the label rather of the image. So what show image just means is the image you want to add and the label of the image. So basically, we're trying to say, okay, this is a grayscale image, and this grayscale image was converted from RGB to grayscale using the RGB to grayscale function. Now, let's move on to NumPy images. Now, NumPy images helps us to do some certain things, or helps us to get some certain information from our image. Now, it helps in image processing also, and one of the things it helps us to do is to flip our image. Now, there's a difference between rotation and flipping. So we can see flipping images like mirroring images. So if you look at this, original dog here and look at the flipped one, you will notice that the right part of the dog is now the left part of the dog, and the left part of the dog is now the right part of the dog. Now, to extract information, we extract information in form of histogram. We can extract information in form of histogram, and it just shows us the feature of the image. And from this feature, we notice that it has more of a green color than any other color. And the green color is not too dark, neither is it too bright, kind of in the middle. That's what this histogram is just telling us. Now, this is image as ND arrays. So most times, so the histogram of an image is the graphical representation of each intensity value, which I already explained here. So the intensity value is like, this is dark, this part here is very dark, this part here is very bright, and this part here is just like grayish in the middle. All right, so let's move on. So aside from Scikit-image, ND, I mean, Matplotlib also has a way of like importing image and getting data from it, or turning it into a ND array. And for us to do that, all you just need to do is you import the image using plt.imageRead, which is imread. Now, this is an image, and the image is an RGB image with red, green, and blue. This here is just like a black and white version of it. But each of these black and white shows the intensity of this, for example, shows the intensity of red and shows just the intensity of red. This here shows the intensity of green, and then this here shows the intensity of blue. And then if you look at the graph, you'll notice that the red is kind of very dark here, but the green is not really dark. But for the blue, we have much more darker blue on in the image. That's what this histogram just helps to tell us. Now, we can obtain colors using NumPy. So when we convert our image to a NumPy ND array, it helps us to extract red, green, and blue from it. And for us to extract it, all we just need to do is we can slice in. So we take the image and then a square bracket, column, then 0. This just helps us to take the red part of the image. And then 1 helps us to take the green part of the image. And then this helps us to obtain the blue part of the image. Also obtain the blue part of the image. So that is the power of NumPy ND arrays. It just helps us to extract more information from the image, which is basically like image processing. So for us to display or show a part of the image you want to see, you can always use this Matplotlib code here. So image show is basically like the code we use to show images or output images on our console, or like the output rather. And also after converting to ND array, you can see the shape of your image, or you can see the exact shape of how the image is. So 423 here is basically showing the height of the image, and then 640 is basically showing the width of the image. So this is the height of the image, this is the width of the image. And then 3 is basically showing that this is an RGB image, which means it has 3 different colors, which is red, blue, and green. That's just what it shows. So we can also see the image size of the image really. And from here we can see that it is 817 920 KB. Basically it should be in kilobyte or byte. Yeah, it should be in byte. This should be byte. That's the size of the image. And we can also flip the image using the np.flip IPUD. So flip IPUD is basically flipping it vertically. But if you want horizontally, there is a different code for that. I think that should be flip LR. ND dot flip LR. That should be. Um. All right. Let's move on. Okay. Yeah. So it's flip LR to flip horizontally. So yeah. What is an histogram? I already said what an histogram is. So the histogram of an image is basically what shows is the graphical representation of the intensity value of the image. And from here, I already explained that 0 means dark and 255 means bright. And from this image, you can see that most of it are very dark. That is why it is skewing to the left side, or is skewed to the left side. And then from here, we see that most of the image here is very bright. That is why it is skewed to the right side of the histogram, which is like 255. Now you can also get the colors of the histogram. And from here, we can see that red is more intense in this image. And then for green, not so much. But for blue, blue is also more intense, but on the darker side. While red is on the like grayer side of it. So what's the application of histogram? Now, histogram helps us to obviously analyze the image. It helps us to also get the thresholding. So thresholding helps us to turn our image to a binary image, which is just leaving it as black and white, at 1 and 0. And it also helps us to show the brightness and contrast of our image. And we can also use it to equalize our image. That is, make sure we get a balanced contrast of what our image should look like. So this is just how we display the histogram or the red histogram in our matplotlib. So you first need to extract the red part of the image. And to extract it, you first need to convert to a ND array, which is done using the plc.imread, then the file you want to, the image file you want to import. And then to extract red, you just say red equals image in brackets and then column column slice column column 0. So this is basically slicing. And what this just does is it takes the red part of the image or the red information of the image. And for us to review it as an histogram, you can just use this code here. So red.rabel is what we use to show it. So why is beam 2556? So basically our beam should be 2556 because the histogram it shouldn't be bigger than 0 to 2550. I mean 255 rather. And that's because like image or most colors are between 0 and 255, which just shows the intensity of a color. Now, visualizing histogram with matplotlib, which is also the same thing here. So this one is to extract the blue. First, you need to extract blue, then you'll be able to get the histogram that you want to see. Now, let's get into one part of image processing in a Scikit-image. So one part of it is thresholding. And thresholding, like I said, is basically like trying to get the binary of your image. You're trying to convert an image to binary. So this is used to partition the image into the background and foreground by making it black and white. So normally this image here, the original image is grayscale. You can't call it black and white. It's grayscale. I'm sure most of us prefer this to black and white on our like normal photos, but it's not black and white, it's grayscale. And the thresholding here is what is the exact black and white because it's just zeros and one. All you can see is black and white. And thresholding is used to partition our image so that we can be able to identify objects in images. So if our if 255, which is white, if the pixels is greater than the threshold, if the pixel is greater than the threshold, it's going to be white. But if it's less than, it's going to be black. So what this is saying is, um, let's say we have a threshold. The threshold can be 20, 30, 50, or in fact 100. If we have a threshold, if that threshold, if our pixels, let's say a part of the image in this image is less than 100, what it means is that it is going to make it black. But if it is greater than 100, it's going to make it white. Now remember, I said 100 is our threshold. So that is why I'm able to get those values. And a lot of times we have global threshold, or we can also identify our threshold or getting optimal threshold so that we can get the exact shape of our image and not get it wrong. And by the way, this image here can be inverted. You can turn the black part to white and you can turn the white part to black. We'll get there. So thresholding is a simple method of image segmentation. What we are basically doing is we're segmenting our image, breaking them into different parts, right? Trying to identify objects and isolate objects, basically. So before we can threshold an image, or before we can get a thresholding of an image, if our image is in RGB, we first need to convert it to a grayscale image before we threshold our image. So these are the basic steps to getting a threshold image. And now, for us to apply it, we first need to get a threshold or identify a threshold. And from this, we identify a threshold of 127. Now, since 127 is our threshold, we take our image and we check if it is greater than our threshold. If it is greater than our threshold, then that part of the pixels is going to be 0. It's going to be white, or 255, which is white. But if it is less than the threshold, it's going to be black. That is how we are able to get this output that we see. And remember, for you to be able to show your image, you just need to, it takes in 2 parameters, which is the image you want to show and then the label of the image. That is why we have here original and then we have here threshold. So for us to invert the threshold, what you just need to do is you need to change, you just change the greater than sign to less than, and it gives you this. Yeah. So before we move on, or before I continue rather, I want someone to okay, let's not, don't worry, let's just move on. So we have different categories of thresholding, and this is one category, but these are 2 categories. We have the global and we have the local. Global can also be called histogram based. This is good for uniform background. Now, what do they mean by uniform background? So we have this image here. Now, if you look at this image, it has a uniform background because there's no a lot of complex parts in the image, which is like the guy is just on black coat and is with some gray equipment, and then the background are just basically gray. So with this, it's easy for us to just threshold it with global, um, the global histogram. And then we have the local or adaptive. Now, this is used for uneven background. So this is an example of uneven background. Now we have a lot of white here, but then the blacks here are like kind of not so clear. But for us to be able to get the exact, the segment it properly, we need to use a local. We need to use a local to like convert it properly, unless we get this blackish thing around it. You guys know about like your printing machine now. There are some printing machine whereby after the print is finished, they get things like this. The reason why they are getting things like this is because the printing machine was not able to segment the image very well, which led to this. So now this is also this is an example of a global thresholding. Now, when we say try all thresholding, this is like trying different types of thresholding. So we have like different types, which is like local, global, and we also have other types, which are here. So we have the ISO data, minimum, obtuse, triangle, mean, leaf, and mean for yen. So all of these are different types of thresholding, and each of these thresholding have their strengths and weaknesses. But depending on the type of images we are using, we we that one will be able to let us know which algorithm itself we should use. So try all algorithm basically is like you using all the algorithm and seeing which one gave the best results. And from what we can see here, Yen gave the best results from the old algorithm we've used. Now for optimal thresholding, we use okay, this one is still global. So basically, just to get optimal thresholding. So instead of you manually putting your threshold value, which was in this place, which was 127, a lot of times it automatically gives a threshold value here. So we can just say the threshold value should just be threshold Otus image. And to get the Otus threshold Otus, you can import it using a Scikit-image filters. Now, here is the result of using a global thresholding, which is an optimal threshold. And if you notice, it gave us a really nice result. And from what we see here, it used something around maybe 90 or 95-ish. I don't know. This is the threshold, this red line right here. But when we used 127, this is what it was giving us. No, this is what it was giving us. It was giving us something more that has like a lot of noise, and we are able to see the image better. So a lot of times, like the optimal threshold might not even be the best, because from here now we notice that you will not be able to identify that this is the water. But yeah, you can see that there's some sort of ripple beside the guy. But yeah, it's not clear. But when we use 127 as a threshold, we're able to see those water, and it's looking like grasses, but we shall know that there's something here, and this is the sky. So yeah, let's just move on. So now when using local thresholding, we use it for uneven images. So local thresholding, you need to first identify the block size. So why do we need to identify block size? So a lot of times, like these images are in pixels, right? And the block size basically identifies which what is what part of the image, or how big should each part of the image I should use look like. So it's like saying how big should my pixels look like. That's what the block sizing just does. That's what the block sizing does. Yeah, so let's move on. Uh, so from here we can see that threshold local takes in like three parameters: the image itself, the block size, and the offset. So the offset is basically like how dark or bright really it is. And from here we are able to identify the threshold, and then we say, okay, if the pixels of the image is greater than the threshold, make it white. If it's less, make it black. That's how we're able to get this. Now it gave us a better segmentation, a better thresholding than the other ones that was used here. So let's move on. I think this is the last part of this part. Okay, okay, this is the last part of this part. So it stops at the thresholding. So I want to move on to the next part. All right, so we're jumping into filtering now. So far, like I just want to ask a few questions and we move on. The most basic question, like, who can tell me what an image is? Hello? Are you guys with me? I'm asking a question. So I've been talking since I just want answers. Who can tell me what an image is?
I think I can take a shot at it. I kind of missed that part, but I know you mentioned it's basically in its most basic form, it's like a series of numbers basically that end up forming what we call the actual image. So it's basically like binary code of a series of numbers, which then when they're put together, then they end up representing the actual image. They end up showing up the actual image. Yeah.
Thank you. Thank you for that. Yeah, you are like close. You are like close, but that one is more like defining a grayscale image or like a binary image, which is like threshold also. Um, an image is an array of matrix. So imagine a matrix. So each of those matrix, you can just see it as a box. You know how matrix is now? We have 3 by 3 matrix. Imagine a 3 by 3 matrix and imagine a part of your image, like just a small part of your image, should be represented as that matrix. Now, in that matrix, we have some series of numbers. Now, this series of numbers shows the color and intensity of that part of the pixels. So this matrix, so basically like the matrix are just the square pixels of the images. And these pixels contain the information about the color and intensity of that image. So basically like that's what an image is. That's what an image is. So I'd like to throw another question. So I've been talking about image processing. Who can mention like maybe 2 or 3 applications where we can use image processing? Okay, maybe I'll just like give an example. So we use image processing in medical image analysis. Who can mention another one?
Can be used in automotive, like in vehicle recognition, license plate
Yeah,
recognition, things like that. Yeah.
yeah, yeah. Thank you very much. Thank you very much. Uh, yeah. So I think it's time to. Okay, someone wants to mention another one. Let's just move on. Let's just.
I so like I want to mention like we use it in object detection like self-driving cars.
Okay. Yes. We use it in surveillance also. That's like security reasons. All these cameras that you see in like offices and stuff, they are doing image processing. So let's jump right in. Now, because so in case you're wondering that, oh, I don't use filter, well, when you go to a studio and you take a picture, I am also a photographer and I take pictures of people. A lot of times I need to add some sort of Gaussian filter or try to make their face smooth so that they look very fine in their picture. And basically what I'm trying to say is filter makes us look pretty or to look funny or to look goofy or to look anyhow we want, in fact scary. And we use filter in things like Snapchat, video calls, WhatsApp, Instagram. We can even use filter right here on Google Meet by filtering our background to make it look like we're in a very nice house or there's just a plain background. Or in fact, we're even in the garden. Those are filters. Now, um, basically what this filter is, according to machine learning, or in machine learning rather, is a mathematical function that is applied on an image. So just like how you take numbers and you perform operations on those numbers, that is how we take images and we perform some certain functions on those images to be able to get a different result from the original one. Now, what does filter helps us to do? Filter helps us to enhance images, emphasize or remove images. And it helps us to smoothen images, sharpen it, and also it helps us to detect edges in the images, which in turn helps in object. So I don't really have much time here because I have like something. So I'll kind of like rush a bit. I just like hope you guys can follow fast. So this one is just like neighbors. Now, this neighbor is basically trying to emphasize on a part of an image and then use that or perform a function on it. So this is an image. Let's say this is our original image. Now, we take that image and then we kind of zoom into it. So this gray part here is what we are seeing here right now. And this is like, almost, why is it kind of hard to explain? So imagine this gray part here is a pixel of an image. We took that pixel of an image and then we try to extract information from it. We try to look at what does it contain. So each of these boxes here just shows the intensity of the image. From here, we can see that most of the part are white and then this part is gray. That's just what it shows. And then now we use it for object detection. We have different type of object detection. We can use scanning object detection. This is Sobel object detection. Sobel object detection looks more blurrish and kind of smooth. While for canning looks more edgy and more like a sketch. But for this one, we use it to identify what that object contains. And from here, it helps to trace the edge of the image. Now, for us to get edges of image, an image is basically like black and white, and the intensity of color is between 0 and 255. And I said 255 is white, 0 is dark, and in between is like grayish. But if you can see here, we have some sort of shadow, edges, light parts, and all of that. That is how it's able to identify edges. Now, we don't need to crack our head and write one mad algorithm or function or whatever. We already have a predefined function that helps us with that. And this is an example, which is Sobel. Now, this is also another example of Sobel. So Sobel just shows a part of the um, image that is like very bright or like very dark-ish and just draw an outline. So boundaries of yeah. And this works by detecting discontinuous in the brightness. So like we can see here, some part of the image have some sort of brightness that has been altered. So those parts of the brightness that has been altered is what it's using to detect the edge. That is why if you can look here, because of some part of the coins have like some figures on it, like 3D figures, that's why it's able to detect the edge. But on this one, there's no 3D figure on this part. So it's only able to detect just the edge of this object and nothing is inside. So now, for us to be able to use Sobel, all we just need to do is we need to just import Scikit-image.filter. So let's just imagine it like saying we open our Snapchat. And in Snapchat, we can just choose different type of filters we want. And one of those filters is Sobel. Now, Sobel uh, just takes in one parameter, which is your image, and it helps us to just trace out the edge of it. Now, you guys can actually try this on your own. You can actually try this on your own in Jupyter Notebook or VS Code. By first installing your Scikit-image. So you can install using pip.install or pip install the name, which is Scikit-image. And you're able to install all those functions that you need in Scikit-image. And then you apply it to your own image, any image at all. But this actually works and is surprisingly very good. So this is still just showing Sobel edge detection. So this is the output we get after writing this code. So the image we used was this coin image, and we're able to get the edge of image. So this is basically what is, okay, this one is different. So we can compare the image using plot comparison. So remember I told you for us to view an image, we use show image, right? But when we want to compare image side by side, that is seeing the original and what filter we've added to it, you can use that by just saying plot comparison. And then you add the first image you want to see, which is the original, and then the one you've applied the filter to, which is the edge Sobel, and then the label of what you want it to be. So basically, it's just edge with Sobel. So that's all. And let's move on. So here's another example of filtering, which is Gaussian filtering. Now, Gaussian filtering is also another function that is used to blur image or reduce the noise in an image. And what it basically is blur edges and reduce contrast. So from this image, if you notice, this dog, some part of it looks kind of very dark and also edgy, and like it's kind of like as if there's a lot of noise inside. Like it is very sharp. Let's put it down. It is very sharp. Now we brought that sharpness down using the Gaussian filter or the Gaussian smoothing function, and it brought it down by a lot actually, by a lot, and giving us this. Can you guys actually see the changes from your end? If you can see the changes, please just react between the two dogs. It's not like a lot, but there's changes. There's a filter applied to it. All right, let's move on. So we have Gaussian smoothing. So this is also an example of Gaussian smoothing. This image is the image of the instructor for this course here, LOL. And then she took a picture of herself and basically took it with Scikit-image. And what she just did was she took an original image that was very sharp and she applied blur Gaussian to make it smoother. And it might not be obvious here, but she now did something. She zoomed in, which gave us this. So if you look at this image here, it looks edgy. It looks very much edgy. But this image looks smoother, giving it more quality compared to this. And this is what happens for photographers here, or for people that edit videos, pictures. When you increase sharpness, this is the results you get. But when you reduce brightness, what you're just doing is you're applying Gaussian blur. That is what you're doing. And for us to apply Gaussian blur, we use the same code. Just like I said, imagine Scikit-image does filter as Snapchat. And in Snapchat, we have like different filters. So this is another filter. Remember the last filter we used was Sobel. Now this is Gaussian filter. And for us to apply Gaussian filter, it takes in two parameters. The first parameter is the image you want to apply that function to. And the second parameter is multi-channel. What is multi-channel? What does multi-channel mean? Multi-channel is basically saying that this image is an RGB color, which means it is not just black and white. It is not grayscale. This is an RGB color. So take note of that. So that's just what it's saying. Let's move on to the next part. Contrast enhancement. Now, for contrast enhancement, they are mostly used in medical images. And that's because most of the time, medical images are not really clear enough after they scan it. So for them to be able to extract information from it, they need to see more part of it. So contrast enhancement is the form of which we see more part of it. Now, what is contrast enhancement? Contrast of an image can be the measure of the dynamic range of spread of its histogram. So it's like I'm taking the dark part of my image and I'm making it darker. I'm taking the brightest part of my image and I'm making it brighter. That is basically what contrast does. It takes the dark part of an image, makes it darker. Takes the bright part of an image, makes it brighter. That is why we're able to see the dark part of this very much clearly here and the bright part of it very much clearly here. And then we're even able to see some hidden parts of the image of this scan here. Now, here is an histogram representation of contrast. Now, in this contrast, we realize that the image have a part of it that's actually very, very bright, which is this part that is like very bright. And then most of it is just grayscale. And then here also, it shows that majority of the images here are very bright. That is why it is skewed down to the right. And because it is skewed down to the right, and because it is skewed down to the right, most of it are actually bright. Now, enhance contrast. Enhancing contrast is basically contrast stretching and histogram equalization. So you guys will get to understand that. So this is it. Remember we talked about global and then local or adaptive category of thresholding. So this is like a grayscale version of it. So histogram equalization have we also have adaptive histogram equalization, and then we have the contrast limited adaptive histogram equalization. So in short, you can just call it clay or clahe or whatever they call it. So these are different types of contrast enhancement, or should I say these are different types of contrast image and make it darker. Now, all of these have some of them have like so we need to also pick a threshold, or should I say, we need to actually identify a point at which the dark part gets darker and the bright part gets darker. So these types here helps us to get an optimal number depending on image we are trying to increase contrast on. Now, we have this image and we are trying to have a good look of what building, which part of them are building, which part of them are trees and all of that, and which part of them is road. This is not clear enough. It looks very faded and too grayish. So we increase contrast and we are able to change the histogram graph or the representation of the histogram, and we skewed it down to the left side and also balanced it, which is like we spread it. So remember I said an histogram, right? Remember I said, no, 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 remember I said, other than spread of the histogram. So let me make that very much clear. So now remember we have this image here, and we have the histogram. Now for us to know what contrast is just how these lines here are being represented. And the more we tweak the lines, the the more the contrast just change. So like if we tweak the line, the contrast changes. That's just what it means. And from here, we notice that most of these images are gray. That is why it is skewed or it is being spread on the gray side. And the gray side is between like 50 and 200, like around that part. But then he also let us know that there's a part of the image that is actually very bright too. So he showed us that there's a part of the image around 250, 255 that is actually very bright. That is why this line is very long. And now we also have this image. Now, if we look at this image very well, they said it's a low contrast image. They said it's a low contrast image. Now, the reason why it is a low contrast image is because the dark part of the image is not even being represented on the histogram. Now, if you look at this histogram, it is being spread to the right side of the image, which means that most of it are white. So we're basically saying, oh, there's no dark part of the image. So for us to adjust it, that is where contrast enhancement comes in. And then we have different types. And those different types helps us to get optimal value of the histogram, which is basically helps us to spread the histogram properly so that the images show properly. So before I move on, I want to know if you guys are actually following and you understand exactly what I'm saying. All right, all right. So before I move on, let me just ask the question. what is a contrast? Or what do you understand by a contrast? Or what do you think a contrast is in your own terms? Like, you don't need to stress your head. Just say what you think. Everybody can unmute their mic and talk. Hello. Please do. I would just like to know that you guys are actually following.
I think for me the contrast would be it's basically the difference in the color that differentiates the image itself from the background of the image. That would be the contrast.
Sorry, can you come again, please?
I'm saying the contrast is the differences in the colors. So for example, we talked about the colors. So the darker colors being from 0, and then the darker colors being the 250. So the contrast is basically that difference of the colors between the image itself and the background of the image.
Okay, so yeah, you are actually close, but let me make that much clearer and like so you can understand it better. So now we have an image here and we have an histogram here, right? In machine learning, like the contrast can be represented in histogram. So it's not really the color or the intensity. That is what is representing. Now, the spread of what the histogram is showing us is basically this contrast. Like, it's not even complex at all. The spread or the representation of the spread of the histogram is basically the contrast. So here's another histogram. Now, I'm trying to like analyze it using the histogram. And from this histogram, I'm able to see that this has some sort of balanced contrast. But in this histogram, I notice that the contrast is not balanced. Why is it not balanced? Because it is not being spread properly in the box. And from what we can see here, it just shows that we don't even have any dark part of the image. It just shows that most of the image are just bright. It's not even dark at all. So contrast doesn't really represent color, but intensity of how bright or dark an image is and how it is being spread in an histogram. That's just what it means. So I'd like to know if you actually understand it better now. All right. Thank you very much. So now let's move on. Let's move on. Yeah. So now we have this image. This is the original image. But for some reason, we feel like we can get more information from this. We can see more details in this image. How can we get those details? By increasing the intensity of the dark part and the light part, we'll be able to see more information on it. But for us to do that, we need to first adjust the contrast. And for us to adjust the contrast, we use a function called the exposure. Now, in Scikit-learn, we can adjust, Scikit-image by saying, okay, from Scikit-image, import exposure. Then you can now say equalize histogram. Now, remember I said that the contrast is basically the spread of the histogram. And we say here, exposure dot equalize histogram. What we are basically saying is, please help us balance the spread of the histogram. So it's like we have this here, and then we are telling, or we are imputing using an algorithm to help us balance the spread so that we can get more of these results rather than something that is just too bright. So this is one of the algorithm we can use, which is equalized histogram. And then what did we get? We got this result. And from this result, we notice that something feels off about the image. Now the image went from being really gray to being very, very black and white. Mind you, this is not thresholding. Remember I said thresholding is more black and white. Mind you, this is not thresholding. But it's just helping us to show more details of what is in the background. But this detail is too much and we are not even able to identify what is in that image. So That is where other types of histogram equalization comes in. And then we have the adaptive equalization. So in adaptive equalization, we have the contrast limited adaptive equalization, which is the Clare that I talked about, which is the type of contrast equalization. So for the contrastive limited adaptive equalization, this is the results we got from that. So if you notice, too it is not too dark here, and it's not too bright here. But from here, you notice it's too bright and it's too dark. But this one gives us more detail. But this one didn't give us more detail. So what I'm just trying to say here is different images have different algorithms that work better for them, which means different images have the kind of or the type of histogram equalization that we use to work better for them. So for this Amotang image, if you notice here now, it's more balanced. We're able to identify the image better, and it has better contrast compared to this that's there. And for us to get that, we use a different algorithm called equalize adapt is. So equalize adapt is like saying, okay, oh, let's look at this histogram. Help us to equalize it based on a part of the image that gives more detail. So it's like adapting to the image itself rather than just using a global threshold or a global distance to get the histogram, to spread the histogram. This one is giving like a more specific one that is better. So, so from this part, if you guys notice, in this adaptive equalize adapt is we have two parameters: the image that we want to balance the contrast, and then we also have the clip limit. Now, the clip limit is basically is normalized between 0 and 1, and the higher it goes, the darker it gets. But the lower it goes, the less darker it gets. So that one just helps us to balance. It's like trying to get a threshold for us. That's what this means here. So let's move on. Let's move on to transformation. And I think that this is where I will stop for today. And that's because I can't like finish it. I have something to do. So for transformation, now transformation is to prepare an image for processing or to analyze or extract data from. Now, transformation uh, is used for classification in machine learning models, and it helps to optimize and compress image. We can use it to optimize image or compress image, and we can also use it to save an image in a particular size. So we can rescale image, resize image, rotate image, flip image, do whatever we want to do with an image. So this is an example of an image, and the image is normal here, but we decided to just turn it to the right side by 90 degrees, and then we just turn it anyhow we like. So a lot of times, sometimes you can get an image that is not this way. So for us to convert it to this way, we need to learn to rotate the image, and that can be done using scikit-learn.transform. So using transform, you can import rotate into it, and it only takes two parameters: the degree at which you want to rotate that image to, and the image you want to rotate. That's what. So this is just how you write the code. It's quite simple. So from all I've been saying, really, a lot of these things are actually very simple. All you just need to do is understand like what you need to do in an image for you to be able to extract information and use that information for something. So we can also rescale image. That is, we take an image that is kind of big with a high resolution, and then we bring the resolution down or like a bit down so that we can be able to have, or so that the image will have less space or doesn't take too much space on our system. So this is basically like rescaling is basically downgrading or upgrading an image. And for us to rescale, you import it using Scikit-image transform, and you import rescale, and it takes in four um, four parameters. The first parameter is the image you want to rescale. The second parameter is how the second parameter is how big or small you want to increase the image. So in this one, we are reducing the image by times 4. That is what this one is basically telling us. And the anti-aliases is basically saying that we want to remove ripple effects in our image. Like, we don't want any ripple effect or wave or our image to look pixelated. So to avoid an image looking pixelated, we add this parameter, which is anti-aliases, and we set it to true. I remember I said multi-channel parameter just means the image is in multiple colors, which is like red, blue, green channel. And that's what this multi-channel is trying to tell the computer. So this is an image, and then we rescaled it down to 800 in width from 3000, which is quite a lot. And that's like basically saying we took it from times 4 times from 1 to less than 1/4. So this is an example of what the aliases that I was talking about is. So this is an original image, and that image is being rescaled. Now, when we rescaled it, it was giving some pixelated wavy ripple effect. So for us to avoid this pixelated wavy ripple effect, that is why we need to specify that the anti-aliases has to be true, which in turn gives us a much more smoother image, which is this. So assuming we didn't have that anti-aliases, it would give us something like this. You look at the image and it looks pixelated. But the one with aliases gives us kind of blurry image, but it's not pixelated at all. That's just the beauty. So rescale and resizing is quite different. So in rescaling, you can identify how like large or how small you want it. But in resizing, you can resize the width and the height. So you can specify, okay, how do you want your width to be? How do you want your height to be? You can specify it to be anything. But in rescaling, it is kind of like locked in. So when you rescale, it still retains the width and height. It just brings the image down a bit, reducing the resolution. So for height, this is what I was saying. You can increase the width by times 2 and then leave the height the way it is. Or you increase the height itself and leave the width the way it is. So you just sort of like, you can stretch the image or like squeeze the image. That's what it just does. So to avoid disproportionality, because from here we can see that image is kind of is not in proportion with the original one. So for us to avoid it, when using resize to scale our image, we use this here. So remember I said that a lot of times, like, for you to be able to extract information from your image, or this is the last thing I'll go and I'll be leaving now. I'm so sorry. You know what? Let me just leave this part because it takes time for me. Before I just leave, I want to know if like you all understand all the things I've said or explained to you. All right. So I just sent the attendance link. You can fill the attendance link. It is is in chat box. But I won't be able to continue anymore. I'm so sorry. Um, but before I go, do anybody here have any question to ask before I go? Does anyone here have any question to ask before I go? Okay, no question. So I'll stop sharing my screen. I'll stop sharing my screen. So I believe like I've kind of explained some certain things that might have been confused to some of you when learning image processing. So I would have to leave now. So sorry about that. I would have to leave now. But you can sign the attendance in the chat box. All right. Uh, does anyone here have anything to say before I leave? Okay. It's the same attendance limbo. Is that all? It's not clickable. It's clickable now. Ah, it's working. Please try again. Oh. I've sent it again. Try again. It's working. Oh. All right now. Um, I'll catch you guys next week. So next week I'll finish up with this image processing, and then we kind of like round up the whole ML scientist track, and then yeah, yeah. So next week we'll basically just round up. Thank you for being here. Yeah, take care. Bye.